Hi. Good afternoon, everyone. My name is Jatinder Mann, and I'm a program manager on the Internet Explorer team, where I'm focused on web performance. I'm also an editor in the W3C Web Performance Working Group, where I work on bringing power and CPU-efficient APIs to the web platform. So for the past few years, the Internet Explorer team has been really focused on making IE fast. And we've learned a lot about web performance along the way. We've learned a lot about how the browser runtime works, how to optimize that browser runtime internally, and how to optimize that browser runtime for current and future performance trends. So I'll share that with you today. We'll also talk about how you can make your sites and apps fast. Okay, so throughout the day, you may have seen this Windows 8 architectural diagram many times. Today, we're going to be focused on two parts of this diagram. The first are traditional web applications. These are applications that run inside your browser, like Internet Explorer, Chrome, and Firefox. It's just the standards-based web. All of the performance techniques we're going to be talking about today apply to the standards-based web. We will also be talking about Windows Store apps, which are also just the web. So all of the performance techniques we're going to be talking about today also apply to Windows Store apps with a few minor exceptions. So a quick show of hands. Who is here today to build faster websites that run on standards-based web browsers? Okay, that's everyone. Who is here to build faster Windows Store apps? Okay, that's most of everyone here too. Excellent. So my goal here is that you leave with two things. First is an understanding of what makes your website, your web application, and your Windows Store app fast. The second is that you will leave here with specific things that you can take, in fact, 50 specific things that you can take and improve the performance of your sites and apps today. So let's start with a couple of numbers. The first is, this is a 300 level talk, and what that means is, if you remember your college days, this will be an advanced look at a subject. So we're going to talk about everything from networking, HTTP, HTML, CSS, JavaScript, JITs, compilers, and everything in between. So we're going to be going very broad and very deep at the same time. Another number that I wanted to throw out there is 200. That's the number of slides I'm going to be showing today. So we're going to be going very deep technically, and we're also going to be covering a lot of material. So my recommendation is that don't take any notes, sit back, relax, try to enjoy hearing me talk for an hour, at least try, and go back home with a few key tips and tricks that really apply to you. And then go check out the video, and then you can review the entire list of 50 tips. Okay, so let's start with a test. Everyone here said that you guys have been building sites and applications and you want to make them faster, so you must have thought about web performance. Let's start with a scenario. I'm originally from Vancouver, Canada, and due to my wife's insistence, I have to visit my mother-in-law for Thanksgiving. Obviously, I'm looking forward to that, and I have to buy round-trip plane tickets. So what I did is I did a little test. I went to the top 5 travel sites based on users. And these are Priceline, Kayak, Travelocity, Expedia, and Orbitz. And I measured how long it took to load the homepage of these sites. Now, the home pages for all these travel sites are very similar. They all have edit fields where I type in where I came from, where I'm going, checkboxes to say whether this is a round trip or a one-way. They have banner ads, they have logos, they have real-time interactive data on the current cheapest flights, special deals. They're all doing analytics. So they're all doing very, very similar things. So you would expect the performance characteristics to also be very similar. So I went ahead and analyzed these sites, and I did this recently, like 2 weeks ago. So we're going to call these sites 1 through 5, because I don't want to poke at any of these sites. Let's keep this exercise anonymous. But if we take a look at a couple of statistics or data points around these sites, so the first kind of dimension we're going to look at is a total number of kilobytes of data that's downloaded when I go and visit these sites. Now you can see that it ranges very significantly. Site number 3 uses 1 megabyte downloaded, whereas site number 1 is 3.7 megabytes. That's almost a factor of 4. If we look at the number of elements in the fully constructed DOM after the page has loaded, we'll see that there's significant variance here as well. We go anywhere from 900 elements to 4,000. Again, almost a factor of 4. If we look at the number of CSS rules in the fully rendered page, again, the data varies from 1,100 all the way up to 5,300, almost a factor of 5. If we look at the number of external image files downloaded, we will see that it's 6 on the low end and 66 on the high end. So that's almost a factor, well, that is a factor of 11. If we look at the number of lines of script downloaded, and this is formatted lines to factor out minification and make sure we're comparing apples to apples, you will see that the number of lines of JavaScript goes anywhere from 10,000 to 77,000. That's almost a factor of 8. And finally, there are very significant differences between how these sites were architected, the frameworks they chose to use, both on the client and the server side. Okay, so we've looked at a couple of data points around all of these sites. Which do you think is the fastest? Anyone? Site number 5, yes. So site number 4 is the most common answer, and that's because people look at the total lines of JavaScript and they assume that the page load is directly correlated with how much script you're running. This actually worked out well for the presentation, that the site that was the fastest actually has quite a bit of JavaScript. Okay, now that you know which is the fastest, which do you think is the slowest? Site number 2. This site doesn't have the highest number of images, script lines, or number of elements. Okay, so what I really wanted to get here is, what is web performance? Web performance is the measure of time from the moment the user takes an action until the results of that interaction, the content, is displayed to the screen. Now, there are 3 key factors to web performance, and the first is network. Network connectivity, network bandwidth. Network is often a very important aspect of web performance. The second is the CPU. How fast can the CPU, your web application, and the browser perform operations? The third is the GPU. We'll get into the GPU a little bit later on, but it's critical to web performance. So as developers, these are the 3 dimensions that we need to focus on when we're trying to improve the performance of our sites and apps. Whether this is a mobile site, a site that runs on your desktop machine, a Windows Store app, these are always the same 3 key dimensions. Okay, so on the Windows platform, you can measure these metrics inside IE or any other browser running on the Windows platform using the Windows Performance Toolkit, which you can get from a free download from Microsoft as a part of the Windows SDK. This tool is fantastic. If you haven't used it, I strongly encourage you to download it and try it out. There's a few links at the bottom of the slide. The first one points to the actual tool, and the second one points to IE blog post that gives you step-by-step instructions on how to use this toolkit to measure browser performance. So you'll be seeing a lot of slides today and a lot of data. All of that data and slides have been gathered using this toolkit. So please feel free to use this and check out the data as well. Okay, so let's look at a CPU chart. This is a CPU chart for loading one of the most popular sports sites on the internet. And again, we're focused on the CPU, so let's take a look at what happens here. So when you type in URL or click on a link, the browser will go ahead and issue a network request. It will go and try to download that HTML document. So you'll see a little spike of CPU activity here. And that's just because the browser just fired off that network request. But quickly thereafter, the browser will be sitting idle again. And that's because there's no work to do here. The document hasn't arrived yet. So the CPU's idle, the GPU's idle, and the network, it's essentially idle waiting for that request. And then a few hundred milliseconds later, that document will come down. And then the browser will start to parse that document. So you'll see a little spike of activity again here. And as the browser is parsing that document, it will encounter sub-resources. It'll encounter CSS, JavaScript, and other sub-resources. And it'll quickly issue those network requests. But relatively soon after that, we're going to be idle again. And that's because we finished parsing the entire page, and now we're just waiting for those sub-resources to download. So you'll see this break in CPU activity. Before finally hitting a point where we have enough resources that are streaming in off the web that we can continue to use the full CPU. So this is a dual-core machine. And when you see that the web platform is fully utilizing, the web application is fully utilizing the CPU, you'll see that we're using one core of the machine. And why is that? That's because the web platform is inherently single-threaded. Now, there are aspects of the web platform, like JavaScript, memory, image decoding, JavaScript memory management, web workers that allow parallelizing some aspects of the web platform. But on the whole, the web platform can only fully utilize one CPU. So when you see 50% here, that means that this web application is fully using the entire CPU. Now, at some point in time, we begin fully processing content because all the content has finished streaming in off the web, and we can start parsing the CSS and the JavaScript and start looking at the images. But oftentimes, in the middle of the page load, you'll see another break in activity. And this is because the page is dynamically requesting more resources. In this particular example, the page actually did a synchronous XHR in the middle of page load. So after that block has been freed, we can start processing content again. And you can see for the next couple of seconds, the CPU is completely pegged. And quickly thereafter, content is displayed to the screen. So from a user's perspective, it feels like now the page is fully loaded. But there's still a lot of activity happening on the page. And you can see for a couple of seconds, there's still CPU activity. Until finally the CPU acquiesces and returns to a regular cadence on updating the page. Okay, so there are 4 key dimensions that I want to talk about. The first is time to glass. This is the amount of time from when the user takes an action until the results of those actions, the content, is displayed to the screen. This is a critical aspect to web performance. That's because it drives a perception of how fast our sites are loading. So we can still be doing work behind the scenes even after the content has been displayed to the screen, preparing for the next set of actions. But it's really important to get the content out to the glass as soon as possible. The second line down is the elapsed page load time. Now, this is the amount of time in milliseconds from when the user clicks on a link or types in an URL until the page is fully loaded and the CPU acquiesces. Within the elapsed page load time, there are 2 other key metrics, and that's CPU time, the third one down. And CPU time is, of the elapsed page load time, how much time is the CPU actually busy? And the fourth one down is how much time is the CPU basically wasted, the idle CPU time. So as web developers, HTML5 developers building this new class of Windows Store apps, our goal is to take these 4 aspects of web performance and push them as far to the left as possible to make our actions feel instantaneous. Okay, so now that we understand that web performance really consists of the CPU, the GPU, and networking, and we have to drive down the CPU time, the question really is, where does the CPU time go? Because it may not just be JavaScript. It may not just be decoding images. Okay, so I thought I would show an architectural diagram of the browser. Now, this architecture is true for even different browsers. We may have different code names, different architectural boundaries, even different names for subsystems. But at the end of the day, all standards-based web browsers do exactly the same thing. So if you were to look at an architectural diagram for another browser, it will look very similar to this. So let's go through each of these subsystems. The first is a core networking subsystem, and it's responsible for bringing down the resources from the network, caching those resources locally, and providing a backup to the browser. The next subsystem is the HTML subsystem. It's responsible for parsing the HTML and representing it as internal data structures as a DOM. The CSS is also responsible for parsing the CSS and representing it in turn in internal data structures as the formatting information. Most browsers have a collection subsystem, and you can think of this as metadata on the site itself, and the browser will use this data during the runtime. Of course, there's the JavaScript subsystem, and it's responsible for parsing the JavaScript, generating bytecode or intermediate languages, and executing that JavaScript. Most browsers also have a boundary between their script engine and the browser itself, which we often refer to as the marshalling tier. And there's time spent in this communication tier talking between the browser and the core web platform. Of course, there's the DOM, and there's time spent in the DOM doing interactions, manipulating nodes, looking up elements. There's the formatting subsystem, and it's responsible for taking all of your markup and all of your CSS and overlaying it on top of each other to format the page. There's the block building subsystem. Now, CSS is inherently a block-based layout model. That means the browser has to build these rectangles every time we're about to lay out the page. And then there's the layout subsystem, and it's responsible for taking these blocks and figuring out the locations, where to put them, and the Z orders for these boxes. And finally, there's the content is rendered to the screen. Okay, so I wanted to go back to the travel sites that we had looked at earlier, and I wanted to look at the breakdown of the time spent within each of these 11 subsystems during the page load. So at the left, you can see this is a scale from 0 to 3.5 seconds, and it's in milliseconds. So looking at site number 1 and starting from the bottom, we can see that gray here indicates the time spent in the networking subsystem. Dark blue is HTML, which is pretty small. And light blue is JavaScript. Pink is the DOM. Yellow, green, and dark yellow is formatting and layout. And purple is rendering to the screen. So looking at all of these sites, you can see that the reason that they're not as fast as they can be is different for each and every one of these. Site number 1 is network bound. It also spends a lot of time rendering to the screen. Site number 3 is JavaScript. Site number 2 is spending a lot of time in all of these subsystems. So as web developers, our job when we're trying to improve the performance of our sites is to really decrease CPU time and increase parallelism within these subsystems. Okay, so if we were to average the travel sites together, you would see something like this. About a quarter of the time is spent in networking. And you see another chunk, 20% of the time is spent in JavaScript. Another large chunk, 20% of the time is spent in layout. 25% of the time is spent in rendering to the screen. So this is why the GPU is so critical to web performance. Now, a common question we get is, great, these are travel sites, that's awesome. What about interactive AJAX sites? What about those? So to answer that question, we took the top 25 AJAX sites like Gmail and Facebook Wall, and we profiled them. And we profiled them in interactive scenarios. So the distribution we got was like so. And the interesting thing is most people associate AJAX performance with JavaScript. They think the faster my JavaScript engine, the faster my AJAX application will be. But that's simply not true. If we look at this graph, you can see that the pipeline between formatting, layout, block building, and rendering, that's the important pipeline. JavaScript actually plays a much smaller role. Okay, so let's jump into the 50 performance tips and tricks. Everything we're going to be talking about today is about decreasing CPU time and increasing parallelism. Now, the 50 tricks are broken down into these 6 principles. I want you to walk away with these 6 principles today. The first principle is to quickly respond to network requests. Okay, if you think about it, when a user goes and types in an URL or clicks on a link, you want to get the content down to the browser as quickly as possible. And the first step in doing that is to avoid redirections. If you're familiar with 300 level redirections, the way it works is the browser issues a GET for URL. And that's going to return a response. And in that response, the server might decide to redirect to another site. Now, this redirection can cause up to 250 milliseconds delay in your application. And now you might think, that gives me a convenience on the server side. I like that. But 250 milliseconds can be up to 10% of your page load time. Now, you might think this is the basics, but 63% of the top websites in the world have a 300 level redirection. That means 63% of the top websites in the world could improve their performance by up to 10% by just not using that redirect. In that same context, avoid meta refreshes. We've all used meta refreshes because we might get lazy, where we drop in an HTML page, and if a user hits that, we just redirect to another site. 14% of the sites on the web, the ones in the Google and Bing search indexes, use meta refreshes. It's an inefficient pattern. Just don't use it. Okay, so after we've avoided our redirections, we want to minimize the amount of time spent on the server to get that initial HTML document back down to the user. Now, we want to get that content back to the user as quickly as we can. And oftentimes, in a web application, when it talks to the server has some work to do. And people often forget to measure this. The server might be talking to a user database and saying, who is this guy, or where is this person coming from, or maybe even logging analytics on that person. In many cases, it may be talking to another database, calculating data. So especially for line of business applications. So all of this time on the server blocks the browser from moving forward. You want to minimize your time there. You want to make sure that you get the content back down to the user as quickly as possible. Okay, when appropriate, use content distribution networks. I'm sure most of you are familiar with CDNs, but let's talk about a scenario. Like if we had a user out in Atlanta, Georgia, and they were talking to a server in Redmond, Washington, if that request was to go straight across the country, it would take 2,500 miles, but it's actually not. It's actually circling through quite a few different routes, sometimes going up through California on its way to Washington. That would be about 3,500 miles, 7,000 miles round trip. So on today's high-speed networks, that's about 250 to 300 milliseconds delay. So what you can do is with CDNs, you can easily geolocate your data closer to your user, especially with static resources. So you can use services like Azure or Amazon or Google services to geolocate your data closer to the user. And essentially, we're just minimizing the amount of time spent on the wire. When people think about networking, they often think about a single pipeline between a server and the client, round-tripping data back and forth. But in fact, the browser can make 6 concurrent connections at a given time. So that means we can download 6 resources in parallel. As a matter of fact, we can do this per domain. So if you were to distribute your content across multiple domains, you can download 12, 18, 24 resources at the very same time. If we think about those travel sites, if they were to distribute their images across 6, 7, or 8 domains and geolocate that user down to the closer to the user, they could get those resources down in a couple hundred milliseconds, deserialized, decoded in parallel, and immediately available. When you're making these connections, make sure to reuse them. So don't send connection closed. You'd be surprised how many frameworks out there send connection closed. Some web servers, in some cases, like Apache, send connection closed. So really make sure to minimize this, to reuse established connections. Know your servers. As web developers, we often link to some cool script out there. We need to understand the performance impact of using that other server. Or what's the service level agreement you have with this other server in terms of performance? You're only as fast as your weakest link. And oftentimes the largest websites in the world don't realize the impact of their weakest link. So really take a look at your resources, see where they're coming from, and try to minimize the impact of slower servers. Understand the breakdown of your network timing. Using navigation timing, resource timing, and user timing, and use standards-based APIs available in modern browsers, IE 10, and Windows Store apps. You can get higher resolution timing information on the navigation of your document, fetching of resources, and developer scripts. So, for example, using navigation timing, I can look at my web application and find out the amount of time it spends in the redirect, app cache, DNS, all of these phases over here. Prior to the timings APIs, this information wasn't readily available. The best a developer could do is to measure the time from the first bit of JavaScript that's executed in the head until the page is loaded. And that does not include the time spent on the server. Okay, so the first principle was about quickly responding to network requests. Principle number 2 is about minimizing the number of bytes being downloaded. The fewer resources you download, the better. So really take a look at all of the resources you're downloading and try to look at where you can cut down. The average website today downloads 777K worth of data. And if we look at this graph, those resources are distributed like so. The vast majority of resources are images, followed by JavaScript and Flash content. The fewer bytes you download, the better. And the best way to download fewer bytes is to gzip your content. Now, because of the servers we're using and because the browsers our customers are accessing our data from, actually often give this to us for free. But as a refresher, the way gzip works is the browser sends a request, and in it says, hey, I support gzip. And then the server sends down an encoded version of your content, which is compressed. And the client will take that content, decode it, expand it to the regular size, and then use it. So again, a lot of us get this for free because of the servers we're using. But a lot of people unintentionally turn off this decoding technique. So take a look. You can confirm by using the Windows Performance Toolkit. Make sure your content is gzipped. Now, the best way to minimize the number of bytes downloaded from the network is to not download anything from the network. In the Windows Store apps that you're building, you can package your resources that you're going to use directly in the AppX package itself. So when the application needs those resources, instead of going to the network, it can pull those resources directly from the AppX package. And in that way, those resources will be available immediately. Now, that's great advice for Windows Store apps. But what about the browser? What about dynamic content? I don't want to package up today's news headlines because it may change. It's dynamic. So for those cases, use HTML5 app cache, a new capability available in IE 10, modern browsers, and Windows Store apps that enable you to put your cache resources locally in your machine. And the way App Cache works is the first time that your web application is accessed, it will go out to the server and it'll pull down those resources directly and persist them in the App Cache. And when your web application needs those resources, it will pull them from the App Cache and not have to hit the network at all. And then the App Cache provides that resources back to the browser. So at a later point in time, you may decide to update your application to V2 or V3. In that case, your App Cache will go to the server, pull down V2 or V3 of your application, and then serve that up to your web application. So once you've implemented HTML5 App Cache, it doesn't have to be aware of the network. It just quickly pulls the resources, and they are available. Provide cacheable content, even if you choose not to implement HTML5 App Cache. When you do provide content, make sure it's cacheable. So when you initiate your request, make sure the response specifies an expiration. And the browser will persist this resource in our temporary caches and serve this up to the application instead of having to hit the network. Oftentimes people say, like, hey, I don't know, I may change my logo. I may change another aspect of my site. Like, I don't want to cache my content. So in those cases, use conditional requests. And the way they work is you mark your content as cacheable, and you specify an expiration. And if the content, if the expiration, if it hasn't been modified since that date, use the one in the cache. And if it has been modified since that date, pull a version from the server. So this is a great way to ensure that your application resources, the ones that don't change, are separated as well from your dynamic resources that do change, and you have safety fallbacks. Make sure you cache your data requests. So today on the web, less than 1% of data requests, such as XML HTTP requests, are actually cached. And we've done some interesting analysis. We've looked at data requests over the course of the day, and we've found in many cases during the day, 95 to 96% of data requests don't change. That means they serve up the exact same data. So you're just downloading the same data, which costs server resources, network resources, and local resources. So you can often do this in some frameworks using a cache-true property. Use standard file capitalization. So this one often catches people by surprise. But essentially, let's think about a scenario. We're downloading an icon here. And the first time we download that icon, we specify the source in lowercase. And at a different part of the page, we think what we're downloading is the same icon, but this time we specify in uppercase. And then there's the careless developer case where I just type it in very quickly. Now the server, it may serve back the exact same file. It may recognize that they're the same files. But from the web platform's perspective, these are 3 different files. These are 3 different network requests. These are 3 different files stored on the machine, which are in fact competing for the resources that we talked about earlier. So really, standardized file capitalization, it can, in many cases, improve your performance. Okay, so principle number 2 was all about minimizing the bytes downloaded from the network. Principle number 3 is about efficiently structuring your markup. So now that we're efficient on the network, let's make sure that the HTML and the CSS that we do download is efficiently structured to be rendered to the screen. Okay, this is my IE-only specific advice, and IE9 and IE10 in particular. So we recommend that you always load your web pages in the latest standards mode. We're fully committed to compatibility. As a matter of fact, you can load content in IE in legacy modes today. You can load it in IE5 Quirks mode, IE7 mode, IE8 and IE9 modes in a fully compatible way. In fact, some of those browser code paths still exist today. But always load your web pages when you can in the latest standards mode, because that will be the fastest mode possible. Now, on occasion, you may have an internal line of business application that needs to run in IE7 mode. You can do that quickly by just specifying a meta tag in the page itself. I don't want to update my application, just use IE7 mode. But the recommended way to do this is to put this information in the HTTP header itself. If you think about it, the browser downloads the content, and when the initial HTML comes down, it starts parsing that content. And it does this in the latest standards mode by default, because it's the fastest. And while it's doing this, it encounters a meta tag, and it realizes, oh wait, I was supposed to do this in the IE7 pipeline. So then it resets the state for the HTML5 pipeline, moves over to the IE7 pipeline, and starts parsing that entire document again. So if you're going to continue to render content in legacy modes, always put that information in the HTTP header. This can save you between 10 to 15 milliseconds. Okay, always link your style sheets at the top of the page. This is an important one. This is often referred to as the flash of unstyled content. Now, if you think back to the web 5-10 years ago, you would often see like content stuttering in, and you would see these flashes of white. Now, we still get that today, but to a much lesser degree. And that's because of the sophistication in the way we structure our markup. So if you put your CSS in the head of the page, the browser will issue that network request first. It will also synchronously block painting until CSS is done. So make sure you put the CSS in the head. That way, images and other things can be downloaded later. never link your CSS at the bottom of the page. We often get emails from people frustrated with their user experiences. They say styles are stuttering in, and it feels like the page just won't complete loading. And more than half of the times, it's because their CSS is at the bottom of the page. So in that case, it doesn't get downloaded until after your images and your asynchronous JavaScript, etc. Okay, when possible, avoid using the @import mechanism for hierarchical style sheets. @import synchronously blocks the creation of internal CSS data structures and painting to the screen. So really, the browser runtime tries to work around this. We have fallbacks, caches, and misses. But really, the best pattern is to just avoid this pattern altogether. You'll be guaranteed better performance. In the same regard, avoid embedding styles inline in the page. So it's very tempting when we're trying to fix that one little bug or change one little aspect of your page to just put that style information directly in the page itself. But what happens is that the browser has to do a context switch. It has to switch between the HTML parser and the CSS parser, constantly going back and forth, back and forth. And that invalidates things like the CPU cache. I've been on a page that had all of its style information inline in the page itself. And by taking all of those styles and putting them in a CSS file and putting that in the head, that improved the performance of that page by 15 to 20%. Only include the necessary styles you need in the page. Many sites have a very large CSS file that's shared across all of their sites. You can think of this as the global style information. We can all be lazy at times and put style information in a place where it's not the most appropriate. In this example, I have styles for the home page and the content page in the same style sheet. The top news sites in the world use this pattern today. In fact, one of the top news sites in the world has one style sheet with 4,000 rules in it, of which only 5 to 10% are used in a single page. What that means for the browser is that the browser has to download all of these styles, parse them, create internal data structures that they'll never be even used. And if you remember that formatting step where we take the formatting information and the DOM and mash it together to get the resulting page, that's slowed down by this as well. Always link your JavaScripts at the bottom of the page. Now, this is a common best practice. And essentially, you want to make sure that the styles and the visuals are downloaded and constructed first. That way, your JavaScript can come later on and manipulate the page how it would like. Always avoid linking JavaScript in the head. This is especially true for older browsers. If you think back to the web 5-10 years ago, if you had JavaScript in your page, that meant that your JavaScript could do something like a document.write and rewrite the entire page itself. So browsers would synchronously block on JavaScript, download it, parse it, create the AST models, and execute it, and then continue parsing the rest of the page. So browsers are a little bit more sophisticated today, but the pattern still applies. In the same context as CSS, avoid inline JavaScript. You have the same context switching issue, but to a much larger degree. Because modern JavaScript engines are trying to build more efficient type systems, and the jitting runtime may not have all the information it needs to make the most effective code. So always put all of your JavaScript in external files. Now, on occasion, you may need to put JavaScript in the head because of a CRM system that you're using or a hosting service. And when you do that, make sure you use the defer attribute on your page. It will help a little bit. But really, just put the JavaScript at the bottom. And even when you do put it at the bottom, if you can, put the async attribute. And what that does is it tells the browser, hey, you can download this JavaScript asynchronously. You can execute it asynchronously. As a matter of fact, with asynchronous JavaScript, you can use patterns where you dynamically add that JavaScript to the page when you need it. Make sure that you remove duplicate code. This one's a bit of an extreme case where I have 2 instances of a jQuery on the page. But 52% of the web has duplicate code. And I'm not talking about a single string manipulation routine. I'm talking about 100 lines or more of duplicate code. So really take a look at your websites. Standardize on a single framework. There's a lot of JavaScript frameworks out there, and a lot of them do a lot of the same things in terms of functionality. Your browser, you may not be using a lot of that duplicate functionality. Sorry, went ahead. You may not be using a lot of that duplicate functionality, but the browser has to download all that JavaScript, has to parse it, construct all these internal data structures. It doesn't know you're not going to execute it. It may even be generating native machine code for all the frameworks that you're adding. So just choose one framework that you really like and stick to it. It will really significantly improve your performance. Don't include scripts to be cool. There are a lot of cool scripts out there, Facebook like buttons, Google Analytics. It's really easy to include one script file that does something cool in the background. But really, that script file, it's running in the context of your page load. So it may not just be heuristics. It may not be loading asynchronously after your page load. It's competing with resources with your page load. So really keep that in mind. Okay. So principle number 4, optimize your media usage. Again, we're responding to network requests quickly. We're minimizing the number of bytes downloaded. We're efficiently structuring our markup. And now we're going to optimize the media we do use in our pages. Okay, so going back to this chart, more than half the bytes downloaded today are images. And on average, websites download 58 images. So be careful to avoid what I call death by 1,000 images. So once you start cropping over 20 to 30 images, you'll start to see a performance impact, possibly, on your page because of the network time. So really take a look at all of your resources and see, do I need these or not? So try to avoid too many images. Especially avoid this pattern. We see this a lot on the web today where at the bottom of your page you're linking to 50 social networking sites. You have these little icons. And each of those 50 icons may be coming from 50 different servers that all impact your load time. Okay, when possible, use image sprites. So I'm sure most of you are familiar with image sprites, but let's look at a scenario. On the left, I have scenario number 1, and I have 6 images here that I'm downloading. There's 6 different connections, and they're being downloaded in parallel, and in total, I use 96K. On the right, I use all these images and I run them through an image sprite tool and I create this one image sprite. And I'm going to use a technique like CSS or some other appropriate technique to lay out these images on the page once I have images down. So in this case, I only use one connection and I download one image, which takes 21K. So by efficiently composing our media in this way, we're improving on all of the performance principles that I talked about today. As a matter of fact, we're especially improving on the GPU, something we haven't touched on yet. On the left, I have 6 images that need memory on the GPU. On the right, I only have 1 image. Okay, when you can, try to create image sprites by hand. So I took a bunch of images, I ran them through an image sprite tool, and this is the output I got. As you can see, there's a lot of wasted space here, and wasted space means wasted bytes on the network. And it also means memory on the GPU that's wasted and local storage. So when you can, try to create the most efficient image sprites possible. And sometimes that means doing it by hand, or at least taking a look at it by hand. As a matter of fact, in this case, the image sprite tool didn't even recognize that the Microsoft logos were the exact same bits. There are a lot of philosophical debates on the web about the best image format to use. My recommendation is to just use PNGs. It's the most efficient balance between compatibility, encoding size, CPU decoding time, bytes required for CPU decoding, and also one of the best compression rates. Just stick with PNGs, and sometimes for photographs use JPEGs, but otherwise just use PNGs. When you include your images, make sure you do so in your native resolution. So in this example, I have an image that's 500 wide by 400 tall, but I'm only using 50 by 40. So I'm scaling it down 10%. Do this in an image program. Do it yourself. That will save you both bytes that you have to download and CPU time. When possible, replace images with CSS3 gradients. So as web developers, we've often taken a 15 wide by 1 pixel wide image and stretched it or skewed it across the screen to create this a gradient effect or some other effect that we like. You know what? With modern CSS capabilities, you can do this directly in markup. You don't need to download that image. You don't need to use the CPU time to do all that processing or all that memory on disk. So in this case, you can use CSS3 gradients to create the exact effect that you like. Also, with modern browsers, you can use CSS3 to do border radius and have the rounded corner effect. So we're all familiar with the pattern, with 9 grids where we take little images to represent different quadrants of a rounded corner. So using border radius, we can do this directly in markup. We don't need to download those images. And the cool thing is you can actually add border radiuses to anything, like divs or CSS3 elements, canvases. It's pretty cool. And in that same context, use CSS3 transforms, to do the move, rotate, skew effect. So instead of having multiple images to create these effects, you can just do this directly from markup to represent those effects. Okay, so for really small images, use data URIs. And the way data URIs work is you just include an image tag as you normally would. And then instead of pointing the source to a file, just point it to a data attribute. And then point it to a base 64 encoded string. So there's a lot of tools out there on the web where you can give it a PNG or a JPEG and it'll give you the string back. So the cool thing about this is you don't have to download that image. You can just do this directly in markup. When you're using SVG, which is a great technology, avoid complex or inefficient paths. Especially if you're looking at the output of a tool like Illustrator, you'll see something like this. It's ridiculously complex. So this takes the browser a long time to download, a long time to parse and construct. So when you can, try to generate the most efficient or least complex SVG. It may be difficult, but generating the SVG by hand may help, or at least proof it by hand. Take a look at it. When you're using HTML5 video, specify an image preview. When you don't specify an image preview, the browser has to download the video, figure out what the first frame is, and then display that to the user. When you do specify the first the image preview, the browser doesn't need to download the video. It just downloads the image, and it doesn't start downloading the video until the user starts using the video. I strongly recommend using HTML5 video over some of the other runtimes out there from a pure performance point of view. And this one often surprises people because there's a perception that these other runtimes are faster in many cases. I've never seen a case where one of these runtimes was faster than HTML5 video. And a core piece that people often forget about is that these runtimes are competing with the same resources as the web platform, the web application itself. So sometimes you see these benchmarks where these runtimes are running very fast. And that's because the runtimes are using up all the machine resources. They're actually blocking the web platform from running. So you don't want to block your users from using your web application. In many cases, you're going to be using very rich media in your applications. Proactively download that media asynchronously. So download it, put it in your app cache or your temporary caches. So when the user does go to click a button, the media is instantly available. Okay, so principle number 5 is write fast JavaScript. Modern JavaScript engines are amazing. JavaScript was cool a couple years ago, but it wasn't fast. Today, all JavaScript engines, they're generating native machine code. They're essentially compilers. So if we take a look at an example here, if we look at the left, we can see code that's in C++, and you can picture this in C or C#. And essentially, it's doing 10 billion loops. And it's doing some add operations. So you can picture this largely as 10 billion add operations. And we're doing the exact same thing in JavaScript on the right, which is a dynamic language. Okay, so let's call that function with an integer argument. And we'll get the results in C++ in 40 milliseconds. That's incredibly fast. If you think about it, there's 1,000 milliseconds in a second. If you asked JavaScript this a couple of years ago, good luck with that. The response will be in 10 minutes or so. But with today's modern JavaScript engines, you'll get the response in 200 milliseconds, which is a factor of 5. Now, if you need to do 10 billion add operations and get the results in 40 milliseconds, you're probably doing cryptography, in which case you should probably use C++. But if you're building real-world applications, JavaScript is incredibly fast. Now, there's one catch that I want to talk about, and that's floating point math. If we pass in a floating point number to this function, C++ would return the results in 40 milliseconds. And that's because it's a static language. It knows a type. It can compile very efficient code. JavaScript, on the other hand, will take 1,600 milliseconds, which is definitely scaled down. Okay, so I won't get into the details of why floating point math is slower, but script engines use a technique called type specialization to know if something is an integer, and they do a lot of tricks behind the scenes. So what we can do in our web applications is, when possible, use techniques like math.floor or math.ceil to convert those floating point numbers to integers, and that will maintain your performance. Now, you don't have to do this everywhere. You only have to do it in those places in your code where you're running in a tight loop. Make sure to minify your JavaScript. Most of you are probably familiar with this technique. Essentially, you take your JavaScript, you remove some characters, and then you simplify your variables. And what you're left with is less JavaScript to download. But there's also a hidden benefit to this, and that's runtime performance. Because we're working with tighter code, smaller variable names, the runtime can more quickly look up variables. So this has both the benefits of download performance and runtime performance. It's actually a great technique. You should also initialize your JavaScript on demand. So don't load your entire JavaScript library during the page load. Do it dynamically, right? Do it when you need to. In this example, I have a variable for something like changing a user tile, which a user doesn't do very often. If that function's called, meaning that the user is changing their tile, inside that function, check this variable to see if the code is loaded or not. And if it's not loaded, go ahead and load the code. So there's a slight delay when the user does change the tile, which doesn't happen very often, but the web application on the whole is much faster. Minimize your DOM interactions. In this case, we have a variable that first calls document. So it crosses over the DOM and grabs document, and then it comes back to the script engine. And as soon as it comes back, it calls body. So it goes back to the DOM and grabs the body. And it goes back and forth, leaving the script engine and coming back. And it keeps doing this constantly, back and forth, back and forth. We did 15 DOM lookups here. So really, cache your variables, cache document, cache body. Minimize the amount of times that you have to leave the script engine. The built-in DOM methods are always more efficient than anything you can write in JavaScript. So in this case, we're doing tree traversal. Using the built-in methods like first child, next sibling, it'll be much faster than anything you can do in a third-party library or in code that you can write yourself. When you need to query a large number of DOM elements, use query selector all. It's faster than anything you can do in script. Inner HTML is a great way to construct your dynamic pages. Now, there's a lot of debate around the semantic value of constructing your dynamic pages one node at a time. A good way to do this is to just pass that in as your markup in as a single string. So pass it into inner HTML, and it can be constructed 10 to 15 times faster in real-world patterns than actually constructing the DOM yourself. In the same context, batch your markup changes. So where possible, batch those strings together, or batch your changes together into one manipulation of the DOM. Okay, maintain a small and healthy DOM. My recommendation is to keep no more than 1,000 elements in your DOM. It will help improve your performance. JSON is always faster than XML. XML is a great data format, but from a purely performance point of view, JSON is always more efficient. Use the native browser JSON methods. Okay, so use regular expressions sparingly. Again, it's a great programming technique. It's pretty cool. But regular expressions take 5 to 6 milliseconds to create and match complex trees. So really, instead of using those 5 to 6 milliseconds, you can use string concats and do that in a few 100,000 cycles instead. Okay, so the last principle, know what your application is doing. And that starts with understanding JavaScript timers. JavaScript timers are programmed through set timeout and set interval. And essentially, it's a pattern where they issue a callback every n number of milliseconds. Most applications on the web today have anywhere between 5 to 10 timers that are running at all times. And about half of those timers are what we call dormant timers. That means they're lost. You have no idea where they are. So make sure you don't have any timers or sequences running that shouldn't be. Right? Make sure you don't have dormant timers. And also combine your application timers. In this example, you can see I have a 6 millisecond timer and a 10 millisecond timer. Why don't I create one timer that manages both, some sort of scheduler? Align your timers that are doing graphics work with your paint beat of the display. So most of us have monitors that refresh at a 60 hertz. And that means they're refreshing every 60 frames per second, which is about 16.7 milliseconds. If you run a set timeout that is updating your thing at 10 milliseconds, that means you're updating at 100 frames per second. That means every third frame is not even being painted. So don't be wasteful. Keep that in mind. An easy way to improve your performance is to look at all of your set intervals and set timeouts and just change them to 16.7. With Internet Explorer 10 and Windows 8 and all other modern browsers, as a matter of fact, you should use request animation frame to do your graphics timer, your graphics work. And what this does is it just returns a callback when the browser is ready to paint. So you don't have to worry about specifying an interval or even worry about using timers. Without knowing the visibility state of your application, you're forced to design your application as if it's always visible. So page visibility is a new standards-based API supported in IE10, the Windows Store apps, as well as modern browsers. And essentially, it allows programmatically for you to determine the visibility state of the application. So when the application is not visible, throttle down activity, save CPU time. This will also help battery life. Okay, so with that, we've covered the 50 performance tips and tricks that the IE team would recommend that you look at when you're trying to improve the performance of your applications. So I want to quickly summarize these 6 principles again. Quickly respond to network requests. Minimize bytes downloaded. Efficiently structure your markup. Optimize your media usage. Write fast JavaScript. Know what your application's doing. Again, all the measurements we collected today were through the Windows Performance Toolkit. You can go download that from Microsoft as a part of the Windows SDK. You can use tools like Xperf and macros that we specify in our blog post that tell you step-by-step instructions on how to use these toolkits to measure your performance today. Again, remember, it's all about network, CPU, and the GPU. It's not about any one of these dimensions. It's about all of these dimensions working well together. I would encourage that you go ahead and play with the IE test drive site. There are a lot of cool performance demos and HTML5 demos to take a look at. Okay, so with that, I would love to take questions after the session's over. So I'm going to be available here. I'd love to hear about your performance issues individually. Also, so this is my last slide. Thank you. Please submit feedback. Awesome. Thanks.